NumPy, or Numpy as some people write or pronounce it, is a linear algebra library for Python. And the reason it's so important for data science with Python is that almost all of the other libraries in the PyData ecosystem rely on NumPy as one of their main building blocks. NumPy is incredibly fast and has bindings to C libraries, and we're going to learn how to work with NumPy arrays as we continue on with this section of the course. As far as getting NumPy onto your computer, it's highly recommended that you install Python using the Anaconda distribution to make sure all the underlying dependencies, such as certain linear algebra libraries, all sync up with the use of a conda install. That means if you have Anaconda as your Python distribution and you installed Python onto your computer using Anaconda, you can install NumPy by just going to your terminal or to your command prompt and typing conda install NumPy. Remember, that's not into Python, that's just straight into your terminal or your command prompt. If you do not have the Anaconda distribution, you can also use pip install to install NumPy. Again, the top conda install NumPy is if you have the Anaconda distribution, and that's the recommended method to install this library. If you do not have the Anaconda distribution, NumPy can also be installed for pip install NumPy. Alright, let's briefly discuss how we're going to use NumPy throughout this section of the course. We're mainly going to be working with NumPy arrays throughout the course. NumPy arrays essentially come in two flavors, either vectors or matrices. Vectors are strictly 1D arrays and matrices are 2D, two-dimensional. But you should also note that a matrix can still only have one row or one column. Let's go ahead and jump to the Jupyter Notebook to get started. Alright, here we are at the Jupyter Notebook. NumPy arrays are the main way we're going to be using the NumPy library throughout the course. And NumPy arrays essentially come in two flavors. They come as one-dimensional vectors or two-dimensional matrices, but they can both be called arrays if they're 1D or 2D. Let's go ahead and show how we can create a NumPy array from Python objects such as a list. I'm going to go ahead and create an object, my list, 1, 2, 3. And if I go ahead and just display that list, notice I get out 1, 2, 3, and it's just a Python list. I'm going to go ahead and say import numpy as np, and then I can call np.array, and now I can cast that list as an array. And notice I get an array back as the container for that list object, and then I can actually assign this and then just call array off of that. So I can cast a normal Python list into an array. And that will return back a one-dimensional array. If I want to get a two-dimensional array or a matrix, I can cast a list of lists. So for example, I can say my underscore mat is equal to a list of 3 lists. So 1, 2, 3, 4, 5, 6, get rid of that extra comma, and then 7, 8, 9. So notice I get back a list of lists, and then if I cast that to an array, I will get back a two-dimensional array. And that's noted both by the way it's presented as the output, but also more importantly as the number of brackets shown on the closing and opening ends of this array. I have 2 sets of brackets which will indicate that this is a two-dimensional array. It has 3 rows and 3 columns. And that's how you can cast normal Python lists or list of lists to a NumPy array. Usually, however, you'll probably be using NumPy's own built-in generation methods to actually create arrays a lot faster and a lot simpler. Let's go ahead and go through some of the most common ways to do that. The most common way you'll probably be creating a NumPy array is using np.arrange. And this is really similar to Python's own built-in range function. You'll go ahead and say np.arrange and then pass in a start and stop. So notice you have a start, a stop, and then a step size as a third argument. And this will return evenly spaced values within this given interval. So if I just say from 0 to 10, but remember, just like in Python's range, its indexing starts at 0, it will go up to, but not including to, 10. I'll get an array back from 0 all the way to 9. So I start at 0, and I go all the way up to, but not including 10, so I get 10 digits back, 0, 1, 2, 3, 4, 5, 6. And this essentially works just as Python's own range function. If I want to go from 0 all the way to 10, I have to say 0, comma 11, and that's what I get back out. And then finally, I can add a third argument, a step size. So if I want all the even numbers from 0 to 10, I could say 0, comma 11, and then add a step size of 2 so that I jump in steps of 2, so 0, 2, 4, 6, 8, 10. That means a range is going to be one of the most useful functions for quickly generating an array using NumPy. If you want specific types of arrays, there's other functions in NumPy that can help us do that. For instance, if we want to generate arrays of all zeros, we can say np.zeros, and you can pass in a single digit to get a one-dimensional vector out, or you can say np.zeros and pass a tuple of the dimensions you want. The first number is going to represent the number of rows, and the second number in that tuple is going to represent the number of columns. So for instance, if I want 2 rows by 3 columns, I pass in the tuple 2, comma 3, and I get back 2 rows by 3 columns. And this is noted by the brackets. Alright, if I want arrays of just pure ones, I can say np.ones, and similarly I can pass in either a single number for a one-dimensional array, or a tuple of dimensions for a two-dimensional matrix. That's ones and zeros. Another really useful built-in function is linspace. And linspace returns evenly spaced numbers over a specified interval. And it's important to not confuse linspace with a range. Here we can see that a range basically returns integers out from a start and a stop in a given step size. What linspace is going to do is it's actually going to take in a third argument of the number of points you want. Let me go ahead and show you what I mean by that. I can say np.linspace, and I'm going to pass in a start, a stop, and as a third argument, I'm going to pass in a number. So let's say I have a start of 0 and a stop of 5. And I want to get 10 evenly spaced points between 0 to 5. I can pass in a third argument 10, and this returns back a one-dimensional vector noted by the one set of brackets here of 10 evenly spaced points from 0 to 5. And I can change this third argument to whatever number I want. So if I want 100 evenly spaced points from 0 to 5, I can just pass that in, and that returns a much larger one-dimensional array. And keep in mind, even though it looks like this is two-dimensional as far as the way it's being printed out, you can tell it's one-dimensional by the fact that there's only one bracket here in front of the array. When you're dealing with 2 dimensions, you'll see that you have 2 sets of brackets on opening or closing at the ends. 3 dimensions will have 3 brackets, etc. Alright, so that's linspace. Again, don't confuse linspace with arrange. Linspace will take in this third argument as the number of points you want. Arrange will take in that argument as the step size you want. Let's go ahead and show how we can create an identity matrix using NumPy. We can say np.eye, and then you just pass in a single digit. An identity matrix, if you're not familiar, is a useful matrix when you're dealing with linear algebra problems, and it's basically just a two-dimensional square matrix, meaning the number of rows is the same as the number of columns, and you have a diagonal of ones, and everything else is zeros. And that's the reason it only takes a single digit as an argument, because identity matrix must be square as the output for np.I. Alright, moving along, NumPy also has lots of ways to create arrays of random numbers, and we're going to use that often throughout the course, so let's go ahead and cover a few ways to do that. What you're going to go ahead and do is call np.random and then the random method. If you click tab, you'll see that there's actually quite a bit of methods, so we're going to go ahead and show you the most common ones. The first one is rand, R-A-N-D. And this is going to create an array of the given shape you pass in, and it's going to populate it with random samples from a uniform distribution over 0 to 1. And that means if I want just a one-dimensional array of random numbers uniformly distributed from 0 to 1, I can pass in a single digit, and I'll get back that one-dimensional array. If I want this to be two-dimensional, unlike the previous functions we worked with, instead of passing in a tuple, I'll actually just pass in the dimensions as separate arguments. So that means if I want a 5 by 5 matrix of random numbers, I just pass in 5, 5 instead of the tuple when working with these random libraries. Alright, if we want to return a sample or many samples from the standard normal distribution or a Gaussian distribution, instead of using rand, we can use randn. And that means I can say np.random.randn, and this will return numbers not from a uniform distribution from 0 to 1, but instead from a standard normal distribution centered around 0. And that means I can go ahead and pass in 2, and I get 2 random numbers from a standard normal distribution. And later on we'll see that plotting these out, not in this lecture, but once we get to data visualization, we'll go ahead and show you a nice normal distribution curve or a Gaussian distribution curve. And again, if I want this to be two-dimensional, I can just pass in 2 dimensions. So for a 4 by 4, I say 4, 4. And no, I don't pass the tuple here, I just pass in each dimension as a separate argument, and I can see by the set of 2 brackets that this is a two-dimensional matrix as an output. And the final random method of creating an array we're going to learn about is randint, and that returns random integers from a low to a high number. I'll go ahead and show you what we can do for that. You'll go ahead and say np.random, pass in randint. You'll pass in, if I go ahead and click Shift Tab here, a low, a high, and then the actual size you want. So for instance, if you just say 1 to 100, you'll get a random integer between 1 and 100. And the low is inclusive and the high is exclusive, meaning 1 has the chance of being selected, but 100 does not. And if you want a particular number of random integers, you can pass them in as a third argument. So if I want 10 random integers from 1 to 100, but not including 100, I can just pass in 10 there, and there are 10 random integers, inclusive on the low end and exclusive on the high end. Okay, let's go ahead and discuss just a few useful attributes and methods of an array. In order to do this, I'm going to go ahead and create 2 new array objects. Let me go ahead and clear this and clear these cells. Alright, I'm going to set ARR as my variable, and I will say this is equal to nparrange 25. So if I check what ARR looks like, here's a one-dimensional array of 0 up to 24. And then I'm going to say ranr is np.random, and it's going to be well, got to put a D there. Random integers from 0 to 50, let's go ahead and get 10 of those. So if I check out what ranr looks like this. You may get different values because it's randomly selected, but you should have just 10 integers there. Alright, one of the most useful methods you can use on an array is the reshape method, and that's going to return an array containing the same data with a new shape. That means I can call my array dot, and then the reshape method on it, reshape, and I pass in the new dimensions I want. So for example, if I want to reshape that array, remember ARR is 25 digits, 0 to 24, I can reshape it as a 5 by 5 array using reshape and then pass in the number of rows you want and the number of columns. Keep in mind, you'll get an error if you can't fill up that matrix completely. So for example, if I wanted 5 by 10, I would need 50 elements to do that. And I'm going to get an error here because the total size of the new array must be unchanged, meaning you need to fill up using only the digits you have, or the elements you have. A nice simple way to check this is that the number of rows times the number of columns is equal to the actual number of elements. So 5 times 5 is equal to 25, and I know I have 25 elements in this array. Okay. Let's go ahead and show a couple more useful methods for finding max or min values or to find their index location. And we'll go over a lot more operations later on in future lectures, but here are some useful ones for you to know. If we go ahead and check out our random array one more time, again, your numbers may be different, but for the sake of this exercise, that doesn't really matter. If you want to find the max value in your array, you can call the max method off of it. And this will return the maximum value of that array. Similarly, if you want to get the minimum value of your array, you can call the min method off of it. If we take a look at the array one more time, we can actually figure out the location of the max or min values by specifying argmax or argmin. Meaning, if I want to actually know at what index value is this max located at, 49, I can say ran r argmax, and that will return the index location of the max value. So I notice that 49 is located at index 3. So 0, 1, 2, 3, I have 49 there. And again, you can do the same thing with the min value. You can say argmin, and it will return the index location of the minimum value. So 6 is the index location of the minimum value, and the minimum value was 3 in this case. Okay, and quickly a few more useful methods and attributes. If you ever want to figure out the shape of a vector, you can say r.shape, and it will return back the shape. Notice here, I get 25, comma, and that's indicating that ARR, that array, was just a one-dimensional vector. If I go ahead and reshape it, so I'm going to say reshape to a 5 by 5, and I'm going to set that equal to R, or ARR. Notice now I have a two-dimensional matrix. If I call .shape off of that, notice I'm not putting parentheses, I'm just calling the attribute off of it. Now it reports back that it's a 5 by 5, so it's two-dimensional now. And the last useful attribute I want to show for now is the data type in this array. If you're ever curious of what data type you have in an array, you can just say ARR and type as an attribute dtype, and it will return the actual data type that's in your array. In this case, it's 32-bit integers. Okay, just as a quick review of everything we've gone over, we've shown you how to create NumPy arrays, either by casting a list to a NumPy array, or by using one of the built-in functions for NumPy arrays, such as arrange, zeros and ones, linspace, and and also the random generation methods. You call np.random, and then rand_n, or randint, or some of the other random methods. Alright, and one last hint I want to show you. If you don't want to have to type in np.random.randint, what you can do is you can say from numpy.random import, and then whatever method or function you wanted to import. So if you wanted to import randint, you could go ahead and do that. And then instead of saying np.random.randint, you can just say randint, and now you have a reference for yourself. There you go. Column. I've already said import numpy as np, and what I'm going to start off with is by creating a sample array. I'm going to say the variable ARR is equal to np.arrange, and I'm just using tab to autocomplete there, and I'm going to go from 0 to 10. And when I say 0 to 10, I mean the actual output. In order to get that output, I'll pass in an 11 up here. So now I have an array of 11 elements that go from 0 to 10. The simplest way to pick out one or some of the elements of an array looks a lot like indexing from a Python list. Basically, you're going to use brackets and slice notation in order to do this. What you go ahead and do is type in the variable name of the array itself, pass in square brackets, and then to get a single value at an index, what you can do is just pass in a number. Meaning if I want the value at index 8, I can pass in 8, and it will return back the value at index 8. In this case, it's actually 8 itself, since I just used arrange to create this array. If I want to get the values in a range, just like a Python list, I can use slice notation, meaning I can say the starting index and the stop index. So if I go ahead and say 1:5, it will start at index 1, which is the number 1, and go all the way up to index 5, which is the number 4, because indexing starts at 0. So to show another example of this, I can say 0:5, and that returns all the values from 0 all the way to index 5. I can also remove the stop point or the start point to go ahead and indicate that I want everything else in the array or everything from the beginning of the array. So for instance, if I want everything up to index 6, Instead of specifying the starting parameter as 0, I can just put a colon and then put 6, and it'll return everything up to the start of the array to index 6. So that's the same thing as saying 0:6. But I save a little bit of typing by just putting in the colon itself. Similarly, what I can go ahead and do is say array, and if I want to start at a particular index and grab everything up to the end of the array, I can use the same notation I did in a Python list by using slicing notation of a colon. Something to note when you're using this notation of a number and then a colon is that you're not actually grabbing at index 5 and beyond, you're grabbing everything beyond index 5, because remember, indexing as far as notation in Python starts at 0. So 5 here is actually at index 6, meaning this notation of 5 colon says grab everything beyond index 5. So that's going to be 5, 6, 7, 8, 9, 10. Because remember, index 5 is actually here at 4, since indexing starts at 0. Here I've grabbed 5 elements, meaning if I say 5 colon, it grabs everything beyond the 5th index, which occurs at 4. And you can go ahead and review Python list slice notation if you want more information about this colon. But essentially this works exactly the same as it does for a normal Python list. NumPy arrays differ from a normal Python list because of their ability to broadcast. Let me go ahead and show you an example of this. I'm going to take my array and grab elements 0:5, so that's going to be 0, 1, 2, 3, 4, and then I can set it equal to the number 100. And what that is going to do, it's going to broadcast that value to those first 5 digits to all be 100. I'm going to go ahead and reset the array, and you'll see why in just a second. If I show the array, I'm back to 0, 1, 2, 3 all the way up to 10. And I want to show you an important note on slices of an array. If I go ahead and create a variable called slice underscore of underscore r for array, and I set it equal to a slice of the array, for instance, 0, 6. So let's go ahead and see that slice of the array. Here we have the array 0, 1, 2, 3, 4, 5, basically that first chunk of the half of the array. If I broadcast on this array, meaning I say slice of array, I use a colon, that means I'm grabbing everything in that slice. If I try to broadcast this to be another number, such as 99, that means when I check slice of array, I see a bunch of 99s. But here's where you have to pay careful attention. If I call back the array, it's actually changed 99 not just on the slice, but on the original array I had called to. So you should note how that change also occurs in the original array, meaning the data is not copied, it's just a view to the original array. And the reason NumPy does that is to avoid memory issues with very large arrays, meaning NumPy is not going to automatically set copies of arrays. If you actually want a copy and not a reference to the original array, what you can do is actually specifically specify copy. So I can do something like this. I can go ahead and say r underscore copy and use the copy method off of the array to specifically indicate that I want a copy. So if I take a look at my array, it's 99999, etc., and then 6, 7, 8, 9, 10. And if I take a look at my array copy, it's also the same thing. But if I do a change to my array copy, maybe by broadcasting every value to be 100, and I check out array copy, every value is 100, but that original array is still unaffected by that broadcasting the command to 100. Go ahead and review the notes on this if this was a little confusing to you, but the basic premise here is that if you actually grab a slice of the array and set it as a variable without explicitly saying that you want a .copy of the array, you should keep in mind that you're just viewing a link to the original array, and that changes you do will actually affect that original array. Okay, let's go ahead and talk about indexing a 2D array, otherwise known as a matrix. I'm going to go ahead and clear all the cells here for a second. Alright, I just cleared all the cells here. And what we're going to do is go ahead and create a 2D array. I'm going to say np.array, and I'm going to pass in a nested list. So I'm going to say 5, 10, 15, 20, 25, 30, and then finally 35, 40, 45. So I'm going to go ahead and show that to the array. And here I have 3 rows with 3 columns. It's 2-dimensional matrix. Great. Alright, there's 2 general formats for grabbing elements from a 2D array or matrix. There's the double bracket format, and then there's the single bracket format with a comma. Let me go ahead and show you the double bracket format, and then I'll show you an example of the single bracket format, which is the format I would recommend to use. But you should know both, just in case you encounter them in the wild. So again, there's my 2D array. Let's say I wanted to grab the digit 5. So that's in the very first, or index 0 row, and in the very first column, index 0. For double bracket notation, I can pass in first the row I want, and then the column I want. So passing in 0, 0 here will return the digit 5, since that's the element in the first row in the first column. What I can do is delete and just do a single set of brackets, and that will index an entire row back. So this will index the entire row of index 0, meaning 5, 10, 15. And if I wanted, let's say, the element 25, well, that's at index 1 for the row, and it's at index 1 for the column. So I can say 1, 1, and this will return 25. What I want you to do is try to see if now you could pause the video and try to grab elements from the array individually using this double bracket notation. Alright, let's say we wanted to grab 40 as just one last example. That's at row index 2, and it's at column index 1. So that's 40. That's the double bracket notation. What you should do, however, I would recommend, is using the comma single bracket notation. And basically what that does is it replaces the double set of brackets with just a comma. And you pass in the row, comma, column number. So for instance, let's say I wanted the digit 30. I would pass in index 1, because it's at index 1 row, and then it's in the third column, so 0, 1, 2. It's in the index 2 column, and that gives me the 30. And that's the same as just saying, whoops, r underscore 2d, and doing it with double brackets. I would recommend that you always use this single bracket with a comma notation, because usually it's less prone to error. Now let's imagine that you didn't want single elements, but actual chunks of this array. For instance, you want submatrices from this matrix. You can use colon for slice notation in order to grab certain sections of the entire 2D array instead of just single elements. I'll go ahead and show you how to do that. I'm going to delete this second cell and show you a couple of examples. Let's say we wanted to grab from the top right corner, meaning I want to say 10, 15, and 25, 30. So this top right corner here is what I want to grab. What I can go ahead and do is use slice notation in order to do this. So I can say grab everything up to row 2, and then grab from column 1 onwards. And that returns 10, 15, 25, 30. Let me go ahead and break this down one more time. As far as the rows, what we're saying is grab everything but not including rows 0 and 1 as the colon, but then don't include 2. So I'm saying slice to 2. And I'll go ahead and show that as just a single command. So if I say colon to 2, that returns these 2 rows, row 0 and row 1. Then, by adding on top of that, I'm saying as far as the columns go, grab everything from column 1 all the way to the end, which basically means just drop over this column 0. And that returns these 2 little subsections, 10, 15, and then 25, 30. Alright, what I would recommend you do now is to, in your mind, grab subsections, for instance, 20, 25, 30, and 35, 40, 45, and see if you can use slice notation along with this single brackets comma indexing notation with Numpy in order to grab subsections of this array. And I encourage you to also see if you can make this array bigger and grab larger subsections. Okay, hopefully you have enough practice with that. If you want more examples, you can always visit the notebook for this lecture, which has a few more examples of 2D array slicing. Throughout the course, we won't do too much of this sort of fancy index slicing, so if this is confusing to you, you don't have to worry about it too much since we won't really actually do it that often throughout the course. We'll usually just grab simple, either single elements or entire rows or columns. We won't usually grab subsections of subsections like we did here. Alright, let's go ahead and move on to the more important method of selection, which you're going to use much more often in this course, which is conditional selection. I'm going to go ahead and create a new array, just a single dimension array, say np.range 1, 11, and check out this array. Okay, so for this array, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What I can do is I can take this array and combine it with comparison operators to actually get a full Boolean array out of this. And what I mean by that is if I compare this to a single digit, for instance, ARR bigger than 5, I will get an array of Boolean values. Notice it says dtype BOOL. So these are true and false values. And it gives me false wherever that comparison was false, and true wherever that comparison was true. And then I can go ahead and save this as maybe bool underscore array. So if I call bool underscore array now, I get back this Boolean array. Now I can use that to actually do conditional selection, meaning I can pass that in to brackets, and I will only get the results where this Boolean array happened to be true. Let's go ahead and break that down one more time. Getting the array and using a comparison operator on it will actually return a Boolean array, meaning an array of all Boolean values. Then I can use that Boolean array to actually index or conditionally select elements from that original array where this happened to be true. So it only returns instances where that Boolean array was true. And more commonly, instead of splitting this up into 2 steps, you would actually do this all in 1 step. You would say array, and in brackets inside of the array, you would pass in the conditional statement, such as ARR greater than 5, and that will return the same answer. And this is the sort of syntax notation we're going to be using all the time as far as conditional selection. So for example, let's say we wanted to know all the elements of the array that are less than 3. What I would do is I would say array, brackets, and then say array less than 3. And that will return all the elements where that is true. And that's the sort of thing we're going to be using a lot in this course, especially when we move on to pandas. This is the sort of notation you should get used to. I know it's a little weird at first to see the variable name inside of itself, but hopefully splitting it up into these 2 steps makes it clear what's actually going on. You're just passing in a Boolean array of values, and then you're just returning wherever it happens to be true at that index of the original array. Alright, that's it for this lecture. What I would recommend doing, as far as an exercise for yourself, is to create a new 2D array by saying np.arrange. We'll go ahead and say 50, and then reshape this to be a 5 by 10. Notice I'm just calling a method off of another method, so this is all one array. And then you have this nice 5 by 10 array, so 0 to 40 and then 0 to 9. And I would recommend for you, just as practice for yourself, try to, in your mind, grab chunks and then see if you can use bracket notation to grab the chunks that you thought of. So for instance, maybe you want to grab here 13, 14, and 23, 24. Let's go ahead and show how we would do that. First, I want to break it up into rows and columns. So 13, 14, that starts at row 0, 1, and then 2. Meaning I want to grab rows 1 through 2. I'm going to go ahead and say 1, and remember with this sort of slice notation you need to go 1 more than you actually need. So I'm saying grab from 1 all the way but not including index 3. So that should be these 2 rows. Let's go ahead and confirm that over here by just saying r underscore 2d and grabbing those rows, 1:3. And this is basically working just like normal Python list notation. So here I have index 1 and index 2, up to but not including 3. And then for the columns, since I want 13, 14, and 23, 24, that occurs at index column 3. Oops. And then I want 4, not including 5, so I'll go ahead and put 5 there. And that returns what we were looking for, 13, 14, 23, 24. I would go ahead and encourage you to practice this by setting up this array in your own Jupyter notebook and then just grabbing chunks of this matrix as you see fit. Alright, so here we are at the Jupyter notebook. We'll go ahead and discuss array with array operations, array with scalar operations, and then some universal array functions, what they are, and how you can find more of them. We'll go ahead and start by saying import numpy as np. And then I'm going to go ahead and make an array. We'll say np.arrange. And let's just go ahead and go from 0, 11, so that way we get digits 0 through 10, so 11 digits from 0 to 10. Alright, you can easily perform array with array operations just by using simple arithmetic signs that you're already used to from Python itself. So for instance, if you wanted to add two arrays together on an element by element basis, you would just say array plus array, and that would add the two arrays together. In this case, I'm just adding an array to itself, so essentially every number's been doubled. I can do the same thing for subtraction or even multiplication. I can also perform array with scalar operations in very much the same manner. So scalars mean just a single number, and what NumPy does is it basically broadcasts that number to every element in the array, so that operation occurs also on an element by element basis. Meaning if I wanted to, here's my array, add 100 to every element in the array, I could just say plus and then the scalar itself. And that would add 100 to every element in the array. And this also works for multiplication, division, subtraction, you name it. So if I want to subtract 100 from every element in the array, I can just say minus 100. Alright, so those are basic arithmetic operations that you can perform with either array on array operations or array with scalar operations. Something I want to show you is that a lot of times NumPy will just issue a warning instead of outputting an error on certain mathematical operations. So for instance, if I try to say 1 divided by 0 in Python, I will get an actual error, a zero division error, which makes sense because you can't divide a number by 0. However, NumPy won't give you the same error. So if I try to say array divided by array, notice the very first element is 0. So I will try to say 0 divided by 0, which doesn't really make sense. However, NumPy will issue a warning. It will say invalid value encountered in true divide here, and it'll just give you a null if you try to divide a 0 by a 0. Everything else is okay. For instance, 1 divided by 1 is 1, 2 divided by 2 is 1 as well, etc., etc. However, on the very first one, 0 divided by 0, it executed and gave you a nan, or null object, back. It didn't actually provide an error for you, meaning you still get an output. And that's important to note the distinction there. That means if you have this sort of operation in your code, you actually won't get an error, the code will continue to run, and instead you'll just receive a warning. If you try to do an operation that divides maybe another number by 0, so for instance 1 divided by 0 instead of 0 divided by 0, you'll also get a warning, but in this case it'll actually show infinity instead of a null. So again, you get a divide by 0 encountered in true divide warning here. However, it still executes the code, and you get INF to signify infinity for the 1 divided by 0 at that very first element. Alright, so that's something to keep in mind as you're working with division and arrays that contain a number or digit 0. And also a quick note is you can also do arrays with exponents by just saying asterisk asterisk, just like you would with Python, and then either the scalar or the array you want. So this is the array to the power of 2. So everything has been squared in the array. Now let's discuss universal array function. NumPy comes with many universal array functions, which are essentially just mathematical operations you can use to perform the operation and broadcast it across the entire array. Let's go ahead and show some common ones. For instance, if you want to take the square root of every element in an array, you can just say np.sqrt and then pass in the array itself. And this will take the square root of everything in the array. Similarly, for calculating the exponential, you can say np.exp and pass in the array. For maximum, you can either say the array.max, or you can also say np.max and pass in the array. That's the same thing as calling the method off of it, which we've seen earlier in the very first lecture on NumPy arrays. You can even do trigonometric functions such as sine, and this will basically pass in every element into sine. And there's cosine, and there's also logarithmic options, so you can say np.log, and if something doesn't work, for instance the log of 0 is technically negative infinity, you'll actually receive a runtime warning divided by 0, but it will give you negative infinity as the answer. If you're wondering where you can find a list of all these universal array functions to reference, you can go ahead and check out the notebook, and it has a link in there for the universal array functions, and it will take you to a link that looks like this. This is the NumPy array documentation here for universal functions, or ufunc. And if you scroll down to the bottom of this page, and again this link is in the notebook for this lecture, NumPy operations, you'll see a whole list of all the universal functions you have available for you. So you have basic math operations, add, subtract, absolute, remainder, etc., log, trigonometric functions, and then some more advanced functions, such as comparison functions, maximum, minimums, floating functions, etc. If it's a very basic or common mathematical function, you should probably visit this page first and see if NumPy already has it built in before you start creating your own function to deal with that particular mathematical operation you were trying to perform on your array. In this lecture, we're going to briefly discuss what Pandas is, how to get it installed onto your computer, and what to expect throughout this section of the course. Pandas is an open source library that's built on top of NumPy, which is why we learned about NumPy first. Pandas allows for fast analysis and data cleaning and preparation. A lot of people like to call Pandas Python's version of Excel, or if you're familiar with R, Python's version of R DataFrames. Python and Pandas really excels in performance and productivity for the user. Pandas also has built-in data visualization features, which we'll learn about once we get to Python for data visualization. Pandas can also work with data from a wide variety of sources. You'll need to install Pandas by going to your command line or terminal, and then use either conda install pandas if you have the Anaconda distribution of Python, or if you install Python through a different method, you can also use pip install pandas. Either one should work for you. As far as what to expect throughout this section of the course, we'll first discuss series and how they interact with pandas. Then we'll build on top of that to go to data frames with pandas. Then we'll discuss some particular topics, such as working with missing data, how to use GroupBy with pandas, merging, joining, and concatenating data frames with pandas, various pandas operations, and then how to get data in and out of pandas for a wide variety of formats, such as CSV files, Excel files, SQL. Series are going to be the first main data type that we'll be working with pandas, and then we'll build off of series to work with data frames in the next lecture. Let's go ahead and get started by jumping to the Jupyter Notebook. Alright, here I am at the Jupyter Notebook. A series is very similar to a NumPy array. In fact, it's actually built on top of a NumPy array object, but what differentiates the NumPy array from a pandas series is that a series can have access labels, meaning it can be indexed by a label. Let's go ahead and say import NumPy as NP, and then I will import pandas as PD. And what we're going to start off with is creating various series from various object types. I'm going to make 4 Python objects. I'll create a list called labels, and this will just be 3 letters or 3 strings in a list, A, B, and C. Then I'm going to go ahead and make a list called my underscore data, and I will say it's 10, 20, 30. Then I will create an object called ARR, and this will be a NumPy array, and I'll just pass in my data. So one is a Python list, and another is a NumPy array. And then finally, as a dictionary, I will pass in A as a key, 10 as a value, B as a key, 20 as a value, and then C as a key, and 30 as a value. And that means I have 4 separate Python objects. I have labels, my list, and then I have my data, I have my array, and then finally, I have my dictionary. Okay, let's show you how you can create a series and what it actually looks like. You can say pd.series, and note here, I'm not actually saving the series to any variable name, I'm just using pd.series. But if you do Shift Tab here, you'll notice PD series takes a wide variety of parameters. We're just going to focus right now on the data and the index, which are the most important ones. First off, we'll just pass in data, and we'll set that equal to my underscore data. We'll just pass in that list. And note here, I get my series back. And it looks a lot like a Numpy array, except here it's very distinguished that we have an index, 0, 1, 2, and then the actual data, 10, 20, 30. And the key to a Pandas series is that you can actually specify what you want that index to be. For instance, I'm going to go ahead and say pd.series. I will pass in data equal to my data, and then I will specify that the index is equal to labels. And remember that's A, B, and C up here. So when I run this, now I have a labeled index series. So I have A as the label, or the index, and then 10 as the actual data point for that index. So unlike a NumPy array, I actually have index that are labeled, meaning I can call these data points using this labeled index. And just as a quick note, since data and index are actually in order as far as placing them in as parameters, you don't have to say data equals or index equals. You could just say my data and then labels as such, and you would also get out a series in the same manner. So you don't need to constantly specify data equals or index equals, as long as you put them in the correct order. Alright, let's go ahead and show you a couple more ways to create a series before we actually start working with data in a series. Another quick way to create a series is by saying pd.series, and you can pass in a NumPy array. And this is going to work exactly the same as a Python list. So here I pass in the NumPy array, and it worked the same way. And just like the list, I could have also passed in labels along with this NumPy array. So essentially a NumPy array is going to work the same thing as a Python list as far as passing it into a series. And then finally, what's really cool is you can say pd series and just pass in a dictionary. And what Pandas is going to do is it's going to automatically take the keys of that dictionary. Let me just go ahead and show it here again. Take the keys of that dictionary, set it as an index, and then set the value of that key to the corresponding data point. So that's a nice fast way to quickly create a series. Alright, something to note here, and another thing that differentiates a NumPy array from a Pandas series, is that a Pandas series can actually hold a variety of object types. Right now we've shown a Pandas series, pd.series, holding just numbers. So for instance, I've shown it holding just an array of numbers, but it could have also hold, as the data, labels itself, which remember is labels, if I go ahead and run this here, is just strings. So a series can actually hold pretty much almost any type of data object with Python as its data point. So it can be strings, and even more interesting than that, we could say data equals, and you could have actually passed in built-in functions. So I could say something like sum, print, len, and it's actually holding references to these built-in functions as data points in this Pandas series. And that's not something you can do with a NumPy array. Now, you'll probably never actually use this as far as hosting functions or references to functions in a Pandas series, but this is just to demonstrate the flexibility of a Pandas series as far as holding different object types. Alright, let's go ahead and move on to actually using an index. The key to using a series is understanding its index, and Pandas makes use of these index names or numbers by allowing for very fast lookups of information, and it works just like a hash table or a dictionary. Let's go ahead and see some examples of how we can grab information from a series. In order to do this, I'm going to create two series. I'm going to make one called ser1 and say pd.series. I'm going to pass in some data. We'll go ahead and say 1, 2, 3, 4, so just a list for my data. And then for the index, I'm going to go ahead and put in some country names, such as USA, we'll put in Germany, we'll put in USSR, and then Japan. So these are kind of like World War II country name references with some values. So I'm going to check out series 1, SER1, and here I have my series. Notice now I have index labels, and 1, 2, 3, 4 are my data points. And note it'll say dtype integer 64 since my actual data points are all integers. Then I'm going to make series 2 in a very similar fashion. I'll say pd.series 1, 2, let's say 5, 4. And then for the index, I'll go ahead and say USA, Germany, and I'm going to on purpose change one of these. We'll say Italy as another World War II country, and then we'll say Japan. And then if I check out series 2, I get 1, 2, 5, 4. So Italy's a little different here and it has a different data point. Now, if I actually want to grab information out of this series, it's going to work very similar to grabbing information out of a Python dictionary. You type in the series, and then as a string, you can go ahead and type in the actual index label, USA. Now, keep in mind, I'm typing this as a string because I know that the index is a string. If I'm working with a series, such as up here, that has 0, 1, or 2, you would just pass it an integer. It depends on what data type is your actual index. Alright. Usually your index is going to be hopefully either a number or a string, so you can either pass in SER1 and then the string, or SER1 and whatever your integer index is. So for example, if I quickly create another series, such as SER3, we'll go ahead and say pd.series, and we'll just pass in the data as labels. If I check SER3, now I have A, B, C as my data points. dtype is an object, which kind of refers to the fact that it's a string, and I can grab stuff out of this by the integer index, which is kind of typically how you would do this for a NumPy array. And then there's the string A returned to me. So you just pass in the actual index label, and it'll return the data that corresponds to that index label. As far as very basic operations to do with a series, they're usually done based off the index. Meaning if I were to say something like SER1, and then we have SER2, and let's say I try to add these. So I say SER1 plus SER2. What's going to happen is it's going to try to match up the operation based off the index. So it's going to say USA is 1 here, and USA is 1 here. So it'll add them up and say, as a result, USA will be equal to 2. Where it cannot find the match, such as Italy, it will put a null. And then USSR is also not in both of them, so it's going to also put a NaN object there. Let's go ahead and see what happens when we run this. And there we see the results. So USA was 2.0, Japan was 8.0, Germany was 4.0, and then where it didn't find the match, it went ahead and put in a null value. Something to note here is that when you're performing operations with a Pandas series, and really pretty much almost any NumPy or Pandas based object, your integers are going to be converted into floats. And that's so you don't accidentally lose information based off of some weird division. And that has to do more with Python 2 and the fact that true division versus classic division is actually differentiated in that older version. If you're using Python 3, you basically don't have to worry about this, but you just have to keep in mind that Pandas and NumPy will always convert stuff to float in order to retain all the information possible. Okay, we'll go ahead and stop here for now and move on to DataFrames, which is going to expand a lot more on the concept of series. In order to fully understand DataFrames, you just need to know the basics of series, which is just that they have a labeled index and then a data point. Really, throughout this course, we're not going to be working too much with series. We're going to be working a lot more with DataFrames, which is the true workhorse of Pandas. DataFrames is going to be their main tool when working with Pandas. Let's go ahead and jump to the Jupyter Notebook to see how it all works. Alright, here I am at the Jupyter Notebook. I'm going to go ahead and say import NumPy as NP and import Pandas as PD. And I'm going to do one last thing here. I'm going to say from numpy.random import randn, and then I'm going to go ahead and set a seed. And what a seed means is just to make sure that we get the same random numbers. That way, if you're following me, you'll see the same random numbers that I see. So you can go ahead and say np.random.seed. Alright, let's go ahead and explore the DataFrame command. I'm going to say df is equal to pd.dataframe, and you can actually use tab here if you're using Jupyter Notebook to autocomplete this. And notice that the F is capitalized. I'm going to do Shift-Tab to check out the doc string and the initial signature for this PD data frame. We have a data argument and an index argument, just like we did for series, but then we have this additional columns argument. Let's go ahead and build this up with some random data, and we'll see what a data frame actually looks like. First thing I'm going to do is pass in that data argument, and I'm actually just going to call rand n 5, 4. And then the next ones we want to pass is the index. And the index, we can just make that a list of characters here. I'm going to go ahead and say A, B, C, D, E. And then finally for the columns, I'm going to go ahead and say W, X, Y, Z. So I'll say W, X, Y, Z. I'm going to go ahead and run this and then pass in the data frame just to display it. And there we get a nice display, and this probably looks and feels a lot like Excel if you're using a Jupyter Notebook, and that's good. If you're using another IDE editor, you may not get such a nice crisp display, but you should get a printed output that looks similar to this. Alright, so basically what we have here is a list of columns, W, X, Y, Z, and corresponding rows, A, B, C, D, E. Now, each of these columns is actually just a Pandas series. So W is a Pandas series, as well as X, Y, and Z. And they all share a common index. And that's basically all DataFrame is. It's just a bunch of series that share an index. Let's go ahead and show how we can use indexing and selection to actually grab one of these series objects, or several of these columns out. One way, and the main way to do this, is by saying df, and then using bracket notation, and then passing in the column name. In this case, let's go ahead and grab the W column. So as a string, I'll pass in W, and this returns the W column. And now take a look at the output. Now this actually looks like a series, and that's because that's exactly what W column is. It's just a series. And you can actually confirm this by saying type of df of W, and it shows that it's pandas.core.series.series. If I just say type on the df object itself, I will get a data frame out. So again, just to reiterate that fact, that a data frame is just a bunch of series that share the same index. Now, there's two different ways you can grab a column from a data frame. The main way, and the way you should always do it, is using this sort of bracket notation and then passing the column name. However, if you're really familiar with SQL, a lot of times when you're selecting a column, you pass in a table, dot, and then the column name. This actually also works for pandas. You could say dot and then the column name. However, I would recommend that you don't use this because it may get confused with the various methods that are available off of a data frame. For instance, if I say df dot and then click tab, I see a whole bunch of methods available for me. And those are a bunch of methods that we're going to learn about as we learn more about pandas. But what may happen is that one of these methods gets overwritten by a column name, and then Pandas is going to get confused whether you're asking for a method or an actual column name. So what you should do to avoid that is always use this sort of bracket notation when requesting a column. Okay, if you want multiple columns back, then you can go ahead and pass in a list of columns. So note that I pass in my brackets, and then I'm going to pass in a list of column names, which is going to result in another set of brackets here. For instance, if I wanted columns W and Z, I pass in a list, here highlighted, W and Z, and I get back a data frame containing those two series. And that means when I ask for multiple columns, I'm actually getting back a data frame. If I ask for just a single column, then I will get back a series. And in the Jupyter Notebook system, that's denoted by the way the output is displayed. Okay, let's go ahead and move on to creating a new column. Pandas supports creation of new columns by just specifying the column as if it already exists. For instance, new. Now if I run this, I'll get an error, and it's a key error. If you scroll all the way down here, it'll say key error, new, and it basically just is trying to tell you that it can't find it, that there is no key new there. However, when you're creating let me go ahead and hashtag that out and put this back in. When you're creating a new column, you can actually define it as if it already exists, and then on the right-hand side of this equal sign, use other columns with arithmetic in order to pull off a new column. For instance, we can say df new column, as if it already exists, is equal to dfw plus dfy, and this will run with no error. And now if I check out df, that new column is actually in place there. And for removing columns, you can say df.drop. You can say df.drop and pass in the actual column name you want to drop. Now, if you just do this by itself, you'll get an error. And let's go ahead and check out what that error is. It'll say value error, and we scroll down, it says labels new, not contained in access. And if I click Shift Tab on the drop method, notice that by default it says access is equal to 0. Access is equal to 0 for the drop method refers to the index. If I actually want to refer to the columns, I need to specify access is equal to 1. And then it will drop that new column here. Now there's two things to note when using this df.drop. The first thing to note is that this doesn't happen in place, meaning I'm not actually affecting this data frame unless I specifically specify this to occur in place. I'm going to go ahead and show you what I mean by that. I've called this line df.drop new access equal to 1. If I call it df, I'll see that I still have that new column. That means I need to actually specify as an argument, and we'll do Shift Tab to show it, the in-place argument. And many Pandas methods will require this in-place argument to be set to true. And the reason Pandas does that is that for you not to accidentally lose information. In case you've done a bunch of adjustments to your data, you don't want to accidentally lose it. So Pandas requires you to say in place equals true if you actually want a lot of these changes to stay and occur in place. And now if I call df by running this cell, notice that new column is now permanently removed because it occurred in place. And something to note here is that we can also use df.drop to drop rows. For instance, let's go ahead and use this to drop the E row. I'll say df.drop, I pass in E, and I can also say access is equal to 0. Now remember, you actually don't have to add that in as an argument, that's the default. So let's go ahead and just say df.drop E, and there we've been able to drop the E, since access is equal to 0. And it works either way. I could say access is equal to 0, and this will work again. And note here, I'm not doing this in place. Okay, sometimes a point of confusion is why are the rows 0 as far as their access, and why are the columns 1? Well, the reference actually comes back to Numpy, since data frames are essentially just fancy index markers on top of a Numpy array. To show this, I can say df.shape, just like we did with a Numpy matrix. And note, df.shape is a tuple for a two-dimensional matrix here, and at the 0 index are the number of rows. So if I say df here, I have 5 rows, A, B, C, and D, E. And then on the index 1, I have 4 columns, W, X, Y, Z, which is why rows are referred to as the 0 axis and columns are referred to as the 1 axis, because it's directly taken from the shape, just as you would with a Numpy array. Okay, now let's talk about selecting rows. We've talked about selecting columns, which you just do by saying df, and in brackets, you pass in the column name. Or, if you want many columns, you pass in a list of the column names, such as Z and then comma X. Let me close off that bracket. So I'm passing a list of column names, and I return a data frame of those multiple columns. Let's talk about selecting rows. I'm going to take a look at my data frame again. Here's my data frame. A, B, C, D, E is my rows. W, X, Y, Z are the columns. There's 2 ways to select rows in a data frame. And you have to call a method off of this, and there's 2 methods to use. One is loc, L-O-C, for location, and this is going to take in a label. So you can also do Shift-Tab here to see this property. And something to note here is I'm using square brackets, which is a little weird, but that's the way it works with Pandas. You pass in .loc, and then you pass in brackets the row you want. For instance, if I wanted the A row, I just pass in .loc, and I pass in the label of that index. And this returns, note, a series. And this comes to our second conclusion that not only are all the columns series, but the rows are series as well, as far as the way they're going to get returned when you request them in Pandas. Now let's discuss the second way to grab a row, which is based off of index position. I can use df.iloc to actually pass in a numerical index position even if my axes are labeled by strings. For instance, if I want C, that row, I can do that two ways. I could either say df.loc for location, and in brackets pass in the row name, which is C, or I can say iloc, which is index-based location, and count what index it's at, so 0, 1, 2, and then on iloc, pass in 2, and this also returns that row. And that basically means you have two ways of selecting rows, using LOC if you want the location or labeled-based index, or iloc if you want the numerical-based index. Okay, let's talk about selecting subsets of rows and columns. And this will actually be very familiar to you since we just learned about Numpy. We can say df.loc if we want to select a subset of rows and columns. We can pass in, just like we did with Numpy, using comma notation, the row we want and then the column we want. So I want the value at row B, column Y. And this returns just a single value there. So if I take a look at my df again, looking at row B, column Y, I have this negative 0.84, and I get the same result here. So just like Numpy, you can use this row, comma, column notation. And if you want a subset of this, you can say df.loc and then pass in a list separated by commas. For instance, let's say I wanted the subset of A, B rows with the WY columns. So basically I wanted this 2.7, 0.9, and 0.65, and negative 0.84. That means I can just pass in a list of the rows I want, which in this case is A and B. And then I can pass in a list of the columns I want. In this case, that's W and Y. Shift enter that, and I get the subset return of the data frame. Okay, let's go ahead and talk about conditional selection. A very important feature of Pandas is the ability to perform conditional selection using bracket notation, and this is going to be very similar to Numpy. For instance, if I use a comparison operator against the data frame, such as asking where is the data frame greater than 0, I will get a data frame back of Boolean values, where it returns true if the data frame value at that point was greater than 0, and false if it was not greater than 0. And this is very similar to the same conditional selection applied to an entire NumPy array, except in this case we're doing it with Pandas data frames. And just like this, we can go ahead and say bool df is equal to df greater than 0, and then say bool df, go ahead and check that out. And here we have our Boolean data frame, and if we pass that in to our original data frame with bracket notation, then we will get out, as a result, values where it was true and nulls, or NaN, where it happened to be false. And that's the way you can use conditional selection along with a data frame. Now usually you probably wouldn't be separating this out into two steps. You would just say df and then in brackets something like df greater than 0, and you would get this result. This sort of operation with a data frame and against a comparison operator isn't that common. What most likely you'll end up doing is, instead of just passing in the entire data frame, you'll pass in a row or a column value. And instead of returning nulls, what that's going to do is return only the rows or columns of the subset of the data frame where your conditions are true. Now let me go ahead and show you an example of what I mean by that. Let's go ahead and take a look at our original data frame. Here we have rows A through E and columns W through Z. What I'm going to go ahead and do is specify df of W greater than 0. And notice I get a series back. True, true, false, true, true. And this is linked to the actual index. And if I take a look at the W column, I see that this corresponds with the W column values. And the value at index C was actually less than 0, so it returns false for being greater than 0. I I can now use this series of Boolean values corresponding to rows to filter out rows based off of a column's value. And that means if I pass in this series into a data frame using bracket notation to say something like df of dfw greater than 0, I will only get back the rows where this happens to be true, meaning I'll only get back the rows A, B, D, and E. It won't return row C since it was false here. Let's go ahead and run that and see what this looks like. Great. And now, since I'm passing in a series, I don't get those null values anymore. You only get those null values when you're doing this sort of condition on an entire data frame. When you're actually passing in conditions based off of columns, you'll just get series values, meaning you'll get only the rows where it happens to be true. And this is the sort of conditional selection we're going to be using most often throughout this course. Let's go ahead and show just a few more examples to really drive this point home. Let's say I want to grab all the rows in my data frame where z is less than 0. So I say df, where df of column z is less than 0. Now let's take a look before we actually run this, what should happen. Well, we'll notice column z, where is it less than 0? Well, that's only occurring in row C. So column z, as in Zelda, and then row C as in cat. Here, this is the only row that should be returned. But remember, we're asking for the entire data frame back, so it should return just this row C for us. And there it is. Okay, great. Now, something else to note here is that when you're doing these sort of commands, let's go ahead and go back to our W greater than 0, you get a data frame in response. And that means you can go ahead and call commands off of this data frame. And you can do this either in one step or two steps. I'm going to go ahead and say result df is equal to this, and then take a look at result df, which is this subset of the data frame without that row C in it. And that means I can go ahead and grab results off of this, such as x. And here I have 4 values of x, A, B, D, and E, based off of this resulting data frame that didn't have that row C in it, as in Charlie. But instead of actually separating this out into two steps, such as grabbing the x column, I can do this all in one step. And let me show you what I mean by that. I can go ahead and say, return the data frame where the column value of W happens to be greater than 0. So return those rows to me. And that means all the rows minus the C row. And since this is a data frame, I can actually go ahead and stack commands such as bracket notation on top of it, such as return the X column where that's true. And now I get the same results as I did up here, except it's all done in one step. And this is something that can be intimidating to beginners at first, since there's a lot of brackets and a lot of stuff going on here. But essentially, this is just, instead of splitting everything up into multiple steps, I'm putting it all into one step. And likewise, since this is a data frame, I can bracket for multiple columns by passing in a list, such as y comma x. And we can see we get a result here. Let me go ahead and break this line down one more time to show the steps that we're taking. First off, we're going to go ahead and say bool df is equal to, well, let's go ahead and say bool series, since that's a little more accurate, is where dfw is greater than 0. So if I say bool series, I get this Boolean series back. Then what I'm going to go ahead and do is say result is equal to df of that bool series. Let's go ahead and check out the result. And it should just be wherever that series was true, which is A, B, D, and E. And there is my result. That's the entire data frame without the row C in it. And then I can go ahead and off of that result, call a list of columns. So we can go ahead and say y comma x. And if we wanted to, we could actually even separate this out into one more step by saying my calls for columns, pass in that list, and then say result of my calls. And we get the exact same thing we have here done in one line, as in multiple lines. That means if you're ever confused on something that looks like this with a ton of brackets and pandas, see if you can break it down into multiple steps if that makes more sense to you. Throughout the course, we're going to be doing this type of notation, these kind of one-liners, And as you get more and more comfortable with pandas, you'll find yourself using these one-liners more and more often. But if you're ever confused, always feel free to break it down into multiple steps. The only disadvantage as far as breaking it down to multiple steps is that you are taking up memory with each variable that you define. So as you get better and better with pandas, you'll want to move towards this simple one-line abstraction of all these commands. Alright, go ahead and pause the video now and really make sure you understand how line in 58 here is the exact same thing as separating it out into multiple lines. Alright, let's go ahead and explore real quick the concept of using multiple conditions, such as 2 or more conditions. Right now, we feel comfortable with doing something like this, which is returning a subset of the data frame based off of one condition. But what if you wanted multiple conditions, such as where w was greater than 0 and y was greater than 1? Well, what you could do is try something like this. Is in parentheses, pass in one condition, and then say and, pass in another condition. And this is going to return an error, and I'm going to do this on purpose to explain why there's an error happening here. And this is a common mistake for beginners to put this and here. And you'll get a mistake that says something about the series being ambiguous. If we scroll down here, we see this. The truth value of a series is ambiguous. And what that is trying to say is that Python's normal AND operator can't actually take into account a series of Boolean values compared to another series of Boolean values. An AND operator can only take into account single Booleans at a time. So true and false returns false, true and true returns true, etc. That means when you pass in an entire series of Boolean values, such as this, the AND operator begins to get confused. It can only deal with these single instances of Boolean values, which is why when you're working with pandas and you want multiple conditions, you actually have to use an ampersand, which is this AND. So that's going to be Shift 7 on your keyboard for most standard keyboards. And notice here that I'm passing these conditions in parentheses to show clear separation between each of these conditions. And then if I run this, I get the row E where this happens to be true. Okay, let's go ahead and break that down one quick last time. When you're trying to use multiple conditions, you can't use Python's normal AND operator. You have to use the ampersand. And then you pass in the multiple conditions in parentheses, and then finally you put it inside of brackets for your data frame. If you want to do an OR operation, you can just replace this with the pipe operator, which is right above your, usually for most keyboards, on your enter key, go ahead and go right above it and then do shift on that backslash, and this should give you the pipe operator. And that's going to be your replacement for OR, because if you try using OR, you'll get the same error. So that's with OR. If I try it with Python's normal OR, again, I'll get the truth value of a series is ambiguous. And that's because you get a series of those values instead of just 1 or 2 Boolean values. Okay, you can go ahead and reference the notes if you want more examples of this, but basically, if you want multiple conditions, pass in each condition in parentheses, and then use an ampersand or pipe operator for the AND or OR. Let's go ahead now and shift gears to talk about index and a little more details about it. What we're going to discuss now is resetting the index or setting it to something else. Let me go ahead and take a look at our original data frame. I'm going to go ahead and clear these cells here by just running them. And let's take a look at our data frame. Again, we have rows A through E and columns W through Z. In order to reset the index back to the default, which is just a range index 0, 1, 2, 3, 4, all the way up to the nth row, what you can do is call the method reset underscore index. And remember to close parentheses that we actually run that method. And if you call that, notice you will get the index reset to a column. And you'll get the actual index then to be numerical. And that's how you can reset the index. Something to note here is just like a lot of other Pandas data frame operations, this doesn't occur in place unless you specify it for it to occur in place. So if I call back df, I still have that original index of labels. If you want this to actually occur in place, what you would just do is say in place equals true and pass it into the reset underscore index. For now, we'll go ahead and not do that. That way we still retain our original data frame. Let me go ahead and clear this out. Again, if you just want to reset the index to a numerical value, you can just use .resetIndex, and your old index will become a column of your data frame. Okay, let's go ahead and show one more new index example, such as setting the index. And in order to do this, I'm going to go ahead and create a new index called new.IND. And I'm going to use a little trick here that I'll explain in just a second. This is going to be a bunch of state abbreviations, and I'm going to say .split on this string. And remember, .split off a string is just a common method for splitting off of blank space, but this is a nice quick way to create a list instead of having to type out every comma. So I'm going to go ahead and set that list equal to new.IND, so I have my new index values here. And what I'm going to do is put this as a column in my data frame. So I'm going to go ahead and say df states is equal to new.IND, and since the dimensions match, so there's 5 items here, it will match from 0 to 4 here on this data frame. So if I check out my data frame, I have this new column called states, CANYWYORCO. Now we know how to reset the index, which is just doing the .reset_index method. But if you have a column in your data frame that you want to be the index, what you can go ahead and do is say .setIndex instead of resetIndex. For example, I can say df.set_index and then pass in the column name you want to be the new index, such as states here. And if I do Shift Enter, now the states column has become the index. Keep in mind, unless you retain this information of the index, this will overwrite your old index and you won't actually be able to retain this information as a new column, unlike reset index that allowed you to have that new column. So that's set index versus reset index. Again, if I check out my data frame here, this wasn't in place. I will need to add the argument, if I do Shift Enter here, in place equals true. A lot of times, when you're using Pandas to read in data, if you have a missing point, what's going to happen is Pandas will automatically fill in that missing point with a null or NaN value. Let's go ahead and explore how we can use methods such as drop_NA or fill_NA to actually drop those missing values or fill in those missing values. Let's go ahead and jump to Jupyter Notebook to get started. Alright, here I am at the Jupyter Notebook. What I'm going to go ahead and do is create a data frame. And just like we could create a series from a dictionary, we can actually create a data frame from a dictionary as well. This dictionary is going to have 3 keys in it. It's going to have key A, key B, and key C. And what these are going to be are columns in our data frame. And then what we can do for the actual data points is pass in a list of values for each key. And those will be the data points for each row in that column name. We'll go ahead and say key A has a list, 1, 2, and then we're going to use np.nan to signify missing or null value. Then we're going to say for key B, it's going to be 5, np.nan, np.nan, and then finally key C, our third column, is actually going to retain all values, 1, 2, and 3. So it has no missing values. And then what we can go ahead and say is df is equal to pd.dataframe, and then pass in the dictionary D. And then when we check out our data frame, we get this nice looking data frame of columns A, B, and C, and then rows 0, 1, and 2. Note, row 0 has no missing values, and column C has no missing values. And then there's a few missing values here in row B, or column B, and 1 missing value in column A. Let's go ahead and explore the drop_NA method. A lot of times, you just want to drop missing values from your dataset, especially if it's just a few missing values. If you say drop_NA just by itself and call it as a method with closed parentheses, what occurs is that Pandas is going to drop any row with any single or 1 or more null or missing values. Meaning, if any of these rows had a null value in it, 1 or more, it went ahead and dropped them. If you want to perform this action, but on the columns, what you can do is check out Shift Tab here and notice that there's an axis argument. That means by default the axis is 0, meaning the operation occurs along the rows. But if you want to do the operation along the columns, meaning drop any columns that have a null value, you can specify axis is equal to 1. And that's going to drop any columns with a null value. Let's go ahead and see the comparison here. And that means df.drop_NA drops any rows with any null values in it. And then df.drop_NA with axis is equal to 1 is going to drop any columns with null values in it. What you can also do is specify a threshold. And if we go ahead and check this out, we'll say df.drop_NA and use Shift-Tab to check out the documentation. Notice that there's a thresh argument. Now what the thresh argument is, it's an integer value. And you will require that many non-NA values in order to not get dropped. For instance, let me go ahead and set the threshold equal to 2. And again, we're just going to do this along the rows. So notice here how we have in row 0, 3 non-NA values. In row 1, we have 2 non-NA values. And in row 2, we have only 1, this number 3, non-NA values. That means if I say drop NA like this, it drops everything but row 0. However, if I set the threshold to be equal to 2 and run this, it went ahead and kept row 1. And basically what that means is because row 1 had at least 2 non-NA values, so 2.0 and then 2, it went ahead and kept that row. Alright, let's go ahead and move on to fill NA. Right now we just focused on just dropping missing values, but a lot of times you'll want to actually replace those missing values. If we take a look at our data frame again, we have these missing values here. If we wanted to fill in those missing values, we can use the fill NA method. And this, if we go ahead and take Shift-Tab here, has a couple different arguments, but notice it has a value argument. And what you can do here is, as a value, set in your fill value. I'm just going to pass in a string to make it very obvious here what's going on. And notice it was able to fill in that value with whatever value we wanted. In this case, just a string that said fill value. However, a lot of times what you're going to want to do is actually fill in the value of maybe the mean of the column. And you can do that, for example, as such. You can say df of A, so that's my A column, and notice I have a missing point here. I'll go ahead and say fill NA, and I will set the value to the mean of that column. And now that value has been filled as the mean of the value. Now there's a whole philosophy and way of thinking and statistical methods for filling in missing values appropriately. I'll let you go ahead and explore those on your own, since they really depend on what kind of data you're working with. For now, all I want you to be aware of is that there's a fill NA method and a drop NA method. To put it simply, GroupBy allows you to group together rows based off of a column, and then perform some sort of aggregate function on them. For instance, in this example here, we have 3 partitions of IDs, 1, 2, and 3, and then we have several values for them. We can group by the ID column and aggregate them using some sort of aggregate function. An aggregate function is basically just a fancy term for any function that takes in many values and then spits out or outputs a single value, such as taking the sum of a bunch of values and outputting the result, or taking the average or standard deviation, etc. These are all aggregate functions, and that's all a GroupBy method does. It allows you to choose a column to group by, it gathers all those rows together based off that column value, and then you perform some sort of aggregate function on it. Alright, with that being said, let's go ahead and learn how to use GroupBy with Pandas. I'm going to go ahead and jump to the Jupyter Notebook. Alright, so here we are at the Jupyter Notebook. I went ahead and copied and pasted this line of data. It's basically just a dictionary from the notebook, and this notebook is just called GroupBy, and it's under the Pandas folder. Okay, you can go ahead and type this out manually, but I would just say go ahead and copy this data. It's just a dictionary, and then you can go ahead and say pd.dataframe, and then pass in that data dictionary, and it should automatically then create a data frame that looks like this. And basically this is just some made up data. We have a company column with 3 company codes, Google, Microsoft, and Facebook. Then we have a person column with a bunch of unique people in it, and then we have some sales numbers, 200, 120, etc. Now what we can do is use the GroupBy method to group rows together based off of a column name. For instance, let's go ahead and group by the company. I'm going to go ahead and say df, and then you say GroupBy, you call it as a method, and you pass in the column you want to group by. In this case, I want to group by the company column. And notice what I get out here. If I just do this, I will get a GroupBy object, and it just points to where it's stored in memory. What I can do is store this as a new variable. So I can say something like byComp for by company, and now I have this GroupBy object. Then the second step of using GroupBy, after you've grouped by that column, is to go ahead and call some sort of aggregate function on it. So for example, if I wanted to get the mean by company, it would look at the sales column and give me the mean or average sale by the company. The reason it can't do this for the person column is because these are strings, and there's no way you can just take the mean of a string. And that means Pandas just automatically ignores anything that's a non-numeric column. Likewise, we can go ahead and perform other aggregate functions, such as sum of everything as far as sales per company. You can even do standard deviations with STD, etc. And you should notice that what I get back is an actual data frame with an index called company and the column value of sales. And that means I could do stuff such as index off of this. So I could say by comp, let's go ahead and sum up all the sales by company. So I have that sum of sales by company, and then I could even call something like .loc FB. And that gives me the sales sum of Facebook. Now, a lot of times, what you're going to be doing is not actually setting this GroupBy object as a variable. You'll probably just call this all in one line once you start getting really comfortable with Pandas. You'll say something like GroupBy company, then you'll call something like sum, and then if you just want it for Facebook, you would call FB. And that's all the same thing, just in one line now. Some other useful aggregate functions that you may find yourself doing are things such as count, which just counts the number of instances per column. And in this case, it was able to return the person column because it's able to count how many instances of a person occur in that column per company. So we have two people and they have two sales each, and that makes sense. You can also do things such as max and min. And note here that it also returns the person because Python is able to store things in alphabetical order, and that's basically what it's trying to show here. The max is the latest towards the end of the alphabet, and if you call min, that's the earliest in the alphabet. So you can see we have A's and C's here. However, you probably shouldn't be using min or max with a string column. You'll probably use all these aggregate functions really with numeric columns. One last useful thing I want to show you with GroupBy is a lot of times you can use GroupBy with the describe method, and that gives you a bunch of useful information all at once. So you can say df.groupby, the company name, and then say describe, and it will give you a bunch of information. So for instance, the count, the mean, the standard deviation, the min, and the max, as well as the quartile values for each company. And if you don't like this formatting, you can actually transpose this. So you can say something like .transpose if you prefer each company to be a column instead of an actual index. So whatever format you like better, you can describe to that. And then you can actually just call column names off of this if you're just interested in a single company or a single column. Alright, that's really it for GroupBy. It's quite basic. You just call the data frame, say .groupby, the column you want to group by, and then whatever aggregate method you want. Remember, it has to aggregate the column values to a single value. And it usually only works on numeric columns depending on what kind of aggregate function you're working with. Matplotlib, or as some people pronounce it, Matplotlib, is the most popular plotting library for Python. And it really gives you complete control over almost every aspect of a figure or plot. And it's designed to have a very similar feel to MATLAB, which is another programming language, and its own graphical plotting capabilities. Matplotlib works very well with pandas and numpy arrays, which is why we're going to learn about it. Later on, we're going to learn about some other libraries, such as Seaborn, that is actually built off of Matplotlib. But in order to understand those libraries, it's important to understand Matplotlib first. You'll need to install it with either pip or conda at your command line or terminal with one of the following commands. If you're using the Anaconda distribution of Python, a simple conda install matplotlib at your command line or terminal should install matplotlib for you. Let's go ahead and jump to the Jupyter Notebook to get started. Okay, let's go ahead and get started with matplotlib. Once you've installed matplotlib, the first thing you're going to be able to do is say import matplotlib.pyplot as plt. And then, if you're using the Jupyter Notebook, what you're going to have to do is say %, matplotlib space inline. And that's going to allow you to actually see the plots you create inside the Jupyter Notebook. Let's go ahead and run this. Great. If you are not using the Jupyter Notebook system, what you're going to go ahead and do is at the end of all your commands for plotting, which we'll show later, what you will type is plt.show, close parentheses. And later on, when we actually start plotting some examples, I'll show you where to actually put that into your code. Alright, let's go ahead and walk through a very simple example using two numpy arrays. I'm going to go ahead and say import numpy as np, and say x is equal to np linspace. So it's going to be linearly spaced. We'll go from 0 to 5 and grab 11 points. And then y is going to be equal to x to the power of 2. So if we take a look at x and y, we have an array from 0 to 5, and then y are just all those elements squared. Now, basic matplotlib commands allow you to very quickly create a plot, and we'll show you two ways of creating matplotlib plots. One is a functional method, and the other one is the object-oriented method. We'll show you the functional method first, and then we'll shift over to the object-oriented method, since that's usually the better way of creating a matplotlib plot. Let's go ahead and show you the functional method first. The functional method is actually quite simple. You say plt.plot, and then we can do shift-tab here, and you're going to pass in several arguments. First one you're going to do for just a basic plot is pass in your x and your y elements, and then we can go ahead and do shift-enter. And here, this will actually show the plot. We've went ahead and plotted x versus y. If you're not in the Jupyter Notebook, which you are going to do at the end of this line, before you run your code, is say plt show. And then if I run that, you can see we get the same plot. You don't have to use plt show unless you're using something that's not the Jupyter Notebook. The difference in the Jupyter Notebook is essentially like you're printing the plot. Notice here, if I don't have plt.show, I get an out cell. If I remove this, or actually put it back in, then I don't get the out cell. That's essentially the same thing, just to do a quick analogy, as typing a string versus saying print the string. And that's the exact same thing what plt.show is doing. It's essentially printing out this plot instead of just showing the plot. Alright, for now on, we won't actually concern ourselves with consistently typing plt.show. However, if you're not using Jupyter Notebook, you will have to keep typing that. So just keep that in mind. Alright, so that's the most basic way to plot something in Matplotlib, which isn't so bad. You can actually add MATLAB-like arguments, such as color and line style, and that will allow you to continue to edit this plot. We'll talk a lot more about this later on as far as line styles and color styles, but if you're familiar with MATLAB, this probably already seems familiar to you. Let's go ahead and remove that for now, and just go with the basics. If we want to add an X label, Y label, or a title to this plot, we can do that with the following methods. We can say plt X label, and then just pass in a string you want for the X label. We'll go ahead and say X label, and then for the Y label, you can say plt.ylabel, pass in a string Y label, and then for the title, you can say plt.title, and then we'll just go ahead and put in a title string there. Let's go ahead and run this. And now we can see we have an X label, a Y label, and a title. And later on, we're going to learn how we can specify the DPI, or dots per inch, in order to get some more clarity here, such as a finer font. Let's go ahead and continue on with creating multi-plots on the same canvas. I'm going to go ahead and scroll down here, remove this cell, and talk about putting multi-plots on the same canvas. In order to do that, we're going to say plt.subplot. And subplot takes in a couple arguments as well. Right now we can't see them, so I'll go ahead and tell you. The first one is going to be the number of rows, the number of columns, and then the plot number you're referring to. In this case, we'll just go ahead and say 1. Then we'll go ahead and plot something on that cell. We'll say XY, and we'll go ahead and specify that it's the color red with the string R as a third argument. And again, don't worry too much about fully understanding this, because once we get to the object-oriented method, a lot of this is going to make way more sense. But I just want to show you what's possible for now. And let's go ahead and say another plt.subplot. We specify 1 row by 2 columns, and the third argument is the plot number. Now we're going to edit the second plot, and we'll say plt.plot. We'll go ahead and do y versus x, and specify b for blue as a string here. Let's go ahead and run this and see what we get. Okay, so now we have 2 subplots here. That's creating multiple plots on the same canvas. Now what we're going to do is, after we've seen the very basics of creating a plot, we're going to break this all down with a more formal introduction to Matplotlib's object-oriented API method. And this means we're going to instantiate figure objects and then call methods or attributes from that object. And that's going to be a much better way of actually using Matplotlib. So the basics for now are just using plt.plot and then putting in your data. Or plt.subplot, specifying the number of rows and columns, and then the figure you're working on, and then using plt.plot. Let's go ahead and switch gears to the object-oriented method. And this is going to be much better. The main idea in using the more formal object-oriented method is to create figure objects and then just call methods off of this. So let me go ahead and show you what I mean by that. I'm going to go ahead and say fig is equal to plt.figure. And I'm going to go ahead and close the parentheses there. Now, if I just run that cell, notice I have a figure object has been created. This figure object, you can think of it as just kind of this imaginary blank canvas, and we can add a set of axes to this canvas. So in the same cell, I'm going to say axis is equal to fig.add underscore axes, and I'm going to add a set of axes. And the way you can add a set of axes is by passing in a list. And the list takes in 4 arguments: a left, bottom, width, and height argument that range from 0 to 1. Basically the percent of that blank canvas you want to go ahead and take. Let me go ahead and show you an example. And again, I'm kind of going to be showing you a lot of stuff that won't make sense at first, but everything will make sense at the end as you see repeated examples and you break it down further. So I'm just typing in some numbers here. This is going to be the left of the axes. This is going to be the bottom of the axes, and this is going to be the width and the height of the axes, 0.8. Let me go ahead and run this on the cell, and now notice what I get here. Now I have a blank set of axes. So I said plt.figure, created a figure object, and then off of that figure object, I called the method add a set of axes and passed in a list of where I actually want the axes to be placed. Next, what I'm going to do is actually plot on that set of axes. And this is going to feel familiar to what we just did earlier. You're going to say axes.plot, and let's go ahead and plot x and y on that set of axes, and then do Shift Enter. And now you can see we've basically come up with the same plot we did earlier, except using an object-oriented method. So if I scroll back up here, this was the plot we did earlier, where we just said plt.plot, but now using this sort of object-oriented method, we're going to have a lot more control over this. It's a little more involved as far as the steps we need to take, but it's definitely worth it. So we've created a figure. We called the figure method add axes on this, passed in a list of axes, and then plotted on that set of axes. If we want to continue by putting X labels, Y labels, and titles, we can go ahead and do that on that set of axes. We can say set underscore X label. It's a little different from the PLT, which is just X label. When you're working with this axes object, you're going to have to say set underscore. And now we can go ahead and pass in the string X label. And you're going to do the same thing for Y labels. Oops. Y label. And let's go ahead and do the same thing for our title. Set underscore title. Now if we run this, we should see our new labels, X label, Y label, and set title. Let's go ahead and continue this idea of object-oriented programming with Matplotlib by putting in two sets of figures on one canvas. And this will start to make sense as far as what this list is referencing. I'm going to go ahead and scroll down to a new cell. I'm going to zoom in a little bit just so we can get a very clear picture of what we're actually doing here. I'm going to say fig is equal to plt.figure. So I'm creating that figure object. So there's my figure object. I'm going to say axes 1 is equal to fig.addAxes. And I'm going to go ahead and set main axes. They will be 0, 0.1, 0.1, and then 0.8, 0.8. And again, this is the left, the bottom, and then the width and height of that set of axes. And then I'm going to add another set of axes. Call them axes 2. I'm going to say fig.add underscore axes. And then what I'm going to go ahead and do is basically put an insert axes. I'm going to say the bottom of this set of axes starts 20% from the left, 50% from the bottom. So excuse me here. I'm talking about basically this bottom corner of the axes, this left and the bottom. So 20% in from the left, 50% up from the bottom, and then we will say it takes up 40% of the canvas size and width and 30% of the canvas size and height. So all these values here must be between 0 and 1. Let's go ahead and run this and note what we get out. We get out this basically insert set of axes, and hopefully now you can begin to see what these values actually correspond to. What I want you to do now is go ahead and pause the video and play around with these numbers. Make sure they're all either between 0 and 1 and see how they correlate with this set of axes. Go ahead and just play around with axes 2 and move it around. For instance, try to get this set of axes 2 over here at this bottom corner. Go ahead and pause the video, see if you can move this insert over to the bottom corner. Alright, I'm going to see if I can do that now. So if I want this at the bottom corner, I probably want to say that it goes left, bottom, width, and height. So I will try shifting it down by making this basically just 0. So let's go ahead and say 0.1 here. Start at 0.15, just a little off the bottom of this insert here, or of axis 1. We'll go ahead and run this. And there I was able to move it more towards the bottom. Remember, this second one's the bottom. And now we want to move it more towards the right, which means from the left, I'll want it to, percent-wise, move this bottom corner more over from the left. Let's go ahead and set this as 8. And now it looks like shifted it a little too much, so let's go ahead and shift it back to maybe 0.5. And there we can see we have it now in the bottom. Alright, go ahead and play around with that. If these figures or these numbers are still a little unclear, remember they're basically just denoting the left, bottom, and the width and height from range 0 to 1 in relation to the blank canvas. I'm going to go ahead and reset these to what we had them at originally, 0.2 and 0.5. So we have our little insert there. And then what I'm going to do is go ahead and plot on these axes. So I'm going to say axes 1 dot plot, and I will say x comma y. And then I will say axes 2 dot plot, and we'll go ahead and say y comma x. Now let's go ahead and run this. And here I can see now I have my little insert and my outer plot. And then I can keep adding stuff on each set of axes. So if I want my insert to have a title, for instance, that's axes 2, I can say axes 2 dot set title, and we'll go ahead and say insert. Well, let's go ahead and make it very clear. We'll say smaller plot. And then on axes 1, let's go ahead and set a title. And we will set this title as larger plot. Let's go ahead and run that. So notice what happened here. I actually got an error because I didn't actually see smaller plot because I forgot to put a 2 here. Let's run this one more time. Okay, now we are getting what we're supposed to get. we have larger plot and smaller plot. And basically, that's the idea behind object-oriented programming with Matplotlib. You create a figure, and that's essentially just an empty canvas. So let me go ahead and show that one more time, just by putting this in a cell by itself. We create this empty figure, there's nothing to show, and then you add a set of axes to it by saying axes, whatever, 1 or 2, etc., equals fig dot add underscore axes, and you pass in this list that goes from left to bottom and then the width and the height in relation to this empty canvas. So if we run this, then we have our empty set of axes, and then you can plot off those axes. You can say axes 1 dot plot and then x comma y. Alright, this is the sort of methodology we're going to be working with for Matplotlib. As far as the very basic way of working with Matplotlib, which is the functional method, you can just say plt.plot or plt.subplot. But we're going to learn how to create subplots using this object-oriented method, which is going to be a lot more efficient and grant us a lot more. The next thing we're going to do is learn how to create subplots using the same object-oriented programming method. I'm going to go ahead and say here, let's just clear everything in this cell. And we're going to go ahead and say this. Let me move this cell to the center, and we'll say fig, comma, axes is equal to plt, and instead of calling figure now, since we're going to try to do subplots, we're going to say subplots. So plt.subplots. Let's go ahead and run this. And notice here we get subplots just out. Now what I can do is just use the axes object like I've done before to plot on it. And this is essentially no different than what we were doing before. And here we said axes.plot, x comma y. Where subplots differs is where you can specify the number of rows and columns. For instance, I can say n rows as my first argument is equal to 1, and n calls as my second argument is equal to 2. And I'm going to go ahead and just show you what that looks like. I'm going to hashtag that out and run this. And now you can see I have one row with 2 columns, and that's basically just a nice front handle on calling plt.figure. All subplots is doing is essentially calling these fig.addAxes automatically for you based off of these arguments of n rows or n columns. Let's go ahead and play around with this. Let's go show one more example. 3 rows by, let's go ahead and say 3 columns. And we can see now we have 3 rows by 3 columns. Later on we'll see how to deal with the issue of stuff overlapping, but it's essentially just a one-line call. We just say plt.tightLayout, and that actually ends up fixing those overlaps. But let's go ahead and take a step back and just work with this 1 by 2. Alright, we have plt.subplots, and essentially it's just an axes manager on top of plt.figure. Something to note here is that instead of just saying fig equals plt.figure, I am doing some tuple unpacking. I'm saying fig comma axes is equal to plt.subplots. And the thing to note about this axes object is if I go down here to this cell and type in axes, axes is actually just an array of Matplotlib axes. Essentially, it's just a list of these axes object, meaning I can actually iterate through it. I can say something like this. For current underscore, ax in axes dot plot x comma y. And I don't actually want to say axes dot plot. I want to say current x dot plot. And then we see that we've actually plotted through this axes. Again, this is just to show that this axes object is essentially just a list of Matplotlib axes, which are the ones that you manually created when you said fig.add_axes. Just further driving the point home that the only difference between plt.subplots and just doing plt.figure is that plt.subplots is essentially doing this add_axes stuff for you automatically based off of how many rows and columns you want. Okay, since we can iterate through this axes object, we can actually also index it, meaning I can say axes 0 dot plot x comma y. And here I've plotted on this first axes, and I can do the same thing for the second one. I can say axes 1 dot plot y comma x. And here we've seen how to either index call off of this axes array or iterate through this axes array. And just like we saw earlier, we can also call titles and labels off of this. So I can say something like axes 0 dot set title. We'll say first plot, and then I will say axes 1 dot set underscore title, second plot. And here we're able to call titles. And you can say set X label, set Y label off of either of these axes objects. All you're doing is just actually grabbing that axes subplot object based off of its position in the array. All right, let's do a quick review of these two object-oriented methods. This first method is a little more manual. It's plt.figure. You go ahead and create that figure. You manually add the axes and choose its location and size. And then, based off of that axes, you go ahead and say .plot and .set title, set X label, set Y label, etc., which we show examples up here. The second method is for subplots that you want arranged by rows and columns. This allows you to call fig, axes, so tuple unpacking here, is equal to the subplots call. And then, based off of those axes, you get an array of axes, and you can plot and set titles either by indexing or by iterating through that axes object. And if you ever have any issues with things overlapping, you can always just say plt.tightLayout, close parentheses, and this will take care of any overlapping plots. I recommend that you just always put this at the end of your plot statements. Okay, now let's start talking about figure size, aspect ratio, and DPI. Matplotlib allows you to control each of these aspects, and you can specify them when you're calling the figure object. Let me go ahead and show you an example. I'm going to say fig equals plt.figure, and the arguments I can pass in are fig size is equal to, and then you pass in a tuple, where the tuple is the width and height of the figure in inches. For instance, I can go ahead and say 3 by 2, and then a second argument you can add is DPI. For instance, 100 DPI, where DPI is just the dots per inch or pixels per inch. I usually just use the default DPI when I'm working with the Jupyter Notebook, so I'm going to go ahead and just clear that for now. I'm going to add a set of axes to this. We'll call it just ax. And we'll say fig dot add underscore axes. And we'll say 0, 0, 1, 1. And then I'm going to go ahead and say ax dot plot x, y. Alright, so there's our plot. Let's go ahead and mess around with the figure size. Let's say we wanted this to be very wide. I could go ahead and say 8 by 2. And now I have this to be 8 inches by 2 inches. Alright, so you can do the same thing with subplots. So I could say plt.subplots, set that fig size. Remember here, now we're going to say fig axes, and I'm going to go ahead and remove the add axes, set the figure size, and set axes. We'll go ahead and plot onto the first axes. I'm going to just say axes.plot xy, and I get a very similar plot. Now I'm going to go ahead and specify some rows and columns for this subplot. We'll say n rows is equal to 1. Let's actually make 2 rows since we're going wide here. And then let's say we have 1 column. So n calls is equal to 1. Now I'm going to call 0 here, plot x, y, and then we'll say axes 1 dot plot y, x. And here we can see the fig size has taken this into account as far as 2 rows by 1 column. And as always, since we have a little bit of overlap here, you should try saying plt.tightLayout. And this will attempt its best to fix out the tight layout. And it looks like it did a pretty good job here. There's some issues here with this y-axis, but we'll show you later how you can customize this y-axis to show a little less information. Alright, now that we've finished discussing figure size and DPI, let's go ahead and make a new cell and begin discussing how to actually save a figure. In order to save a figure, you can use Matplotlib to generate just high-quality outputs in a number of formats, including PNG, JPEG, EPS, SVG, PGF, and PDF. To save a figure to a file, you can use the SaveFig method. So for instance, we have our figure here that we already created. Remember, that's just right here, fig. And then I can say fig.save fig, and all you have to do is pass in the file name you want. So for instance, my_picture, and then you pass in the extension, and Matplotlib is smart enough to know what you want. So if you want a PNG, you just say .png. If you want a JPEG, you say .jpeg, .jpg, etc. Let's go ahead and save this as .png, and that will automatically save the figure. Here you can also specify the DPI. So if you forgot to specify the DPI over here when you were actually creating the plot, you can specify again the DPI over here. So you can do this with like a 200 DPI. Then you can increase the DPI as you want more detail. Alright, we've already gone over figure titles and axes labels, such as set the X label and set the Y label, but let's show you a quick reminder of how to do that. I'm going to change this back to just a simple fig equals plt.figure. We'll go ahead and add a set of axes to this. So we'll say fig.add_axes. We'll put them at 0, 0, 1, 1, and then we'll say x.plot x, y. Alright, so as a reminder, if you want to add a title, you take one of these axes and you say set title, and you just pass in a string of the title you want. In order to set a Y label, you just say set Y label, pass in a string of the Y label you want, and then for X label, you can do the same thing. Set the X label you want. Okay, so I have my title, my Y label, and my X label. Let's talk about legends. With legends, you can use label text to actually clarify what plot is what plot. And I'll show you what I mean by that. I'm going to go ahead and remove these 3 lines of code and say x.plot y, x. So notice I'm just doing this on the same figure, meaning if I say and actually run this, I will get 2 lines here. I will get the xy plot and the yx plot. Since these are quite different, let's go ahead and get something that's a little more similar. I'm going to go ahead and plot x versus x squared and x versus x cubed. Alright, so now we have 2 lines here, and if you were just looking at this figure by itself without being able to reference the code, you're probably a little confused as to what each plot represents. You would want to add in a legend. And in order to add in a legend, it's actually quite simple, but it's a 2-step process. The first step is to just call ax.legend at the bottom of your code where your axes are defined. And if you run that, you will notice you get a warning. It says no labeled objects found. And that's where the second step comes in. For each of these plot calls that you just made, you're going to add in an argument called label. And this label is just a string that you want for the ax.legend function to be able to reference. Let's go ahead and show you what I mean by that. We can go ahead and say x squared here as our label. And then in this label, I'm going to go ahead and say x cubed. And now when I run this with ax.legend, I see I've been able to create a legend. So all this does when you call ax.legend is it looks for each of the plot calls and then checks to see if there's a label. And then this label, which is just a string, gets returned and gets matched up to the correct color of your line. Let's go ahead and talk about setting colors with Matplotlib. So I'm going to go ahead and just say fig equals plt.figure. And then I'm going to go ahead and add a set of axes to this figure. Ax is equal to fig.add_axes. And I will set this at 0, 0, 1, 1. And then, whoops. And then off of that set of axes, I'm going to say ax.plot and do x, y. And this is a reference to the same x and y that we've been working with. So if I go ahead and plot that, I get something that looks like this. Now I can edit this color of the plot by putting in the color parameter. And the color parameter can actually take multiple arguments. It can take in arguments such as common color strings, like blue, or let's go ahead and put in orange. And we can see we get an orange line out, or green, and you get a green line. So very basic color names it can actually accept as a string. If you want to start getting more detailed, you can actually put in RGB hex codes. So I can put in hashtag and then some RGB hex codes, such as, let's go ahead and just copy this from the notebook, FF8C00. Oops, 8. And that gets you a more custom color. So you can go ahead and Google search for RGB hex code, maker, or creator, and you should have plenty of tools available freely online for actually coming up with these RGB hex codes in case you want to make a very custom color. But for very basic colors, basically kind of Crayola colors, such as purple, you should be able to easily plot them and just pass in the string. Okay, so that's the basics of colors. Now let's talk about line width and line style. If you want to edit the line width, you can actually just pass in line width as an argument and just put in a number. So for instance, if we put in 1, that is the essentially default line width. If we want to go double the default, we can say line width is equal to 2, and that will double the width. And we can continue doing this. So if I want a very thick line, such as line width equals 20, that's 20 times the thickness of the default line. Or if you want a very thin line, such as half the default thickness, 0.5, you can start getting thinner and thinner. Another very useful tip as far as line width and line visibility is the alpha argument. So I'm going to go ahead and set my line equal to line width 3, and you can specify the alpha argument, which allows you to basically control how transparent the line is. So I can say alpha is equal to 0.5. And if I run that, now you can see we actually have a little bit more transparency on this line. So you can combine color, line width, and alpha in order to get the exact appearance that you want. One last thing to note here is for shorthand, you actually don't have to type in line width completely. You can just type in LW and it will still work just fine. Okay, so we talked about line width, color, and alpha. I'm going to go ahead and remove the alpha call. Now let's talk about line style. So I can type in line style. And line style, there's quite a few options and they're listed in your notebook, but it basically just defines the style of the line, such as a dashed line or a dotted line. For instance, if I pass in 2 dashes, I end up getting a dashed line. I'm just passing this in as a string. Or if I pass in a dash and then a period, I get this sort of dashed line. So dash point, and then there's a couple of more options such as colon, which gets me these smaller dashes here. And you can check out the Jupyter Notebook for this lecture to see what other options you have. And then you can also do steps. However, I rarely use those. Most often I'll just either do a dashed line, or if you just put in 1 dash, it's just a solid line. Okay, and just like with line width, you actually don't need to type in line style. You can just put ls, and it will end up working just the same. Okay, so we talked about line width and line style. Now let's talk about markers. So markers are going to be used when you have just a few data points. For instance, if we take a look at x as a reminder of what it is, we can see that x is just an array of, go ahead and check the length of x, of 11 points. Let's say I actually wanted to mark where those 11 points occurred on this plot. Well, I can specify marker as a new argument, that should be a comma, and then I can pass in a string. So there's lots of possible marker symbols, and they're listed in your notebook, but the most basic one and common one is just this lowercase o as a string. And there you can begin to see some dots that basically mark out each point on x versus y here. And there's a wide variety of markers available to you. They're all listed in your notebook, but just to show you a couple, you can do things such as plus signs, which don't show up too well here. You can do things such as little stars, like asterisk symbols. You can do things such as passing in these number codes. I'm going to make the line width a little thinner so you can actually see these markers here. Let's say we wanted to make these markers bigger. Well, you may have guessed that marker size is an argument. So you can go ahead and specify marker size and essentially just 1 is the very small size, and then if we want to make it quite a bit larger, we can say 10, and here we can begin to see these kind of triangles begin to form. So let's go ahead and say just huge markers at 20. And then we can specify marker type, here, 2, we can say plus, we get these pluses here, etc. So all these options are listed in the documentation, and more importantly, in your Jupyter notebook, since there's so many different types of strings you can pass in as marker for marker codes. And if you really want to customize your markers, for instance, let's go ahead and hook this back to lowercase o so we get these points here. I'm going to change this line width back to 1. There's actually quite a few options as far as specifying what the marker looks like. You can specify the marker face color, the marker edge width, and the marker edge color. So for instance, I'm going to go ahead and add these arguments in. So just press comma enter for a new line, and I'm going to go ahead and say marker face color. And you can specify the marker face color. So that'll be the color inside of that circle. Let's go ahead and make it yellow and run this. And that changed the marker face color. Let's say I want to change the marker edge width. I can go ahead and edit that as well, make that a little thicker, such as 3. That makes it a little thicker. And let's say I actually want to specify the color of the marker edge. I can specify marker edge color. And let's go ahead and make that green. Alright, so we can see there's a lot of customizability here, and there's a lot of options. If you want to see a bunch of examples of different options, you can go ahead and jump to the Jupyter Notebook for this lecture. I'm going to go ahead and do that now. Just going to go ahead and click on over. And if you see here under the Matplotlib Concepts lecture, right now we're in this section, line marker and line and marker styles. Here there's basically a figure where we did 12 by 6 on these subplots as far as figure size, and did a bunch of plots and edited the colors, the line widths, the line styles, and here's just a bunch of examples so you can go ahead and read them out. And if you're looking for different possible marker symbols, they're all here as comments or line style types, etc. So there's a lot of different examples here that you can kind of copy and paste from or build your own knowledge off of. Finally, let's talk about control over axis appearance and plot range. And if we hop back over to our original notebook over here, we can go ahead and show how we can set the Y limit and the X limit. I'm going to make this just a very simple plot again. Let's go ahead and just make this line width equal 2, and let's make line style equal some dashed line. Okay, great. Let's say I only wanted to show the plot between 0 and 1 on the x-axis. Well, to do that, you can just call your axis, and then say set underscore xlim, and then you pass in a list with a lower bound and an upper bound. So we'll go from 0 to 1. And here we can see we've set the lower bound and upper bound of the x-axis. Now let's go ahead and do the same thing for the y limit. Just call your axis and then say set underscore ylim. And as a list, you pass in upper bound and lower bound. So lower bound at 0, comma, let's make the upper bound. Let's go ahead and just put it at 2. And now we can see this plot. And notice as we zoom in, the plot looks more and more like a bunch of straight lines connecting points, which makes sense because we don't have as much detail since there's only 11 points. As we zoom out, we see more of a curved line. And we can fix that by getting more data points or by zooming out. Control.